Boa tarde a todos, sean bienvenidos a la sesión 18 do Seminário de EDP y Matemática Aplicada. Aproveito la ocasión para enviar un grande saludo a la Universidad Nacional Mayor de San Marcos, mi alma mater, que el 12 de mayo cumple 470 años de fundada y también hace parte de la organización del seminario a través de la profesora Rosana López. A continuación paso la palabra a la profesora Sandra Malta para presentar al profesor Puel. Adelante, Sandra.
Okay, Juan, thank you. For me, it's an honor and a privilege for me to introduce my dear friend Jean Pierre Puel, professor at the University de Versailles, Saint-Quentin. Puel has and had many collaboration in several countries, such as China, Chile, Spain, Mexico, and also in Brazil, where he was for several periods as a visiting professor at UFRJ via the Science Without Borders program, and later he spent a period at UFPE. Puel has received several awards in his career, advised numerous theses, and collaborated with many well-known mathematicians in the field of PDE. Among them, we can mention, for example, Professor Henrique Fernandes Cara here, Carlos Conca, Carolina Fabre, and Lúcio Borcardo, and so on. Therefore, it's an honor for us to have Professor Puel deliver a lecture at our seminar. So, Puel, please, the word is now with you. Thank you very much for being here.
Thank you so much, Sandra, and for the introduction. And okay, everybody hears me correctly?
Yes,
it's
yes.
Okay? Okay.
For me, it's okay.
So I will try to explain the work that we did with Felipe Chavez and Mauricio Cardoso, who are attending this lecture, I think. And this was a result of a collaboration when I went to Recife a few years ago, and then we continued the problem. So I will, the outline is standard, and I will try to explain first the problem on the wave equation, and then at the end of if I have time, I will try to explain what happens for Schrodinger equation, which is a little bit different. Okay, so the motivation is the starting goal was proposed by Mauricio, and it was to try to concentrate the prescribed value of the energy in a given subdomain for systems driven by Schrodinger or by the wave equation. So, of course, to do that, you have you need an action on the system. And the action, you call it control, or you call it action, for example. And, okay, so we have to perform an action on the system. And for simplicity here, we will consider actions inside the domain, but we could also take action on the boundary values, control, on the part of the boundary of the physical domain. Okay, we will see that it happens that this question turns out to be equivalent to a localized controllability problem. I will explain that. So first of all, I explained that on the wave equation. So as usual, I take the physical domain omega to be a bounded set of Rn. And the little omega is an open subset of omega, and T is positive. And we consider the wave equation, the wave equation here. And you have, at the right-hand side, you have a control. Acting chi omega is the characteristic function of omega. So the control acts only on the part little omega and during the time 0t. The boundary conditions are Dirichlet boundary conditions for y, so y0 on the boundary, and the initial conditions are y0 and y1. And we assume that y0 is in the Sobolev space H10 and y1 in L2, and this is correct for the wave equation. And V, the control, the action, is in L2 of 0t and little omega. Okay, now this is the wave equation, standard wave equation. Now we have the domain D, a subdomain of omega, capital D, and we define the localized energy of y in D. So the localized energy is this one. So I call it E sub D of y at time t is the energy, the classical energy of the wave equation, the velocity, 1/2 of the velocity in L2 square, plus 1/2 of the gradient of y in L2 square. But L2 of D only, L2 of D. So not L2 of omega. Okay? And the question is, given, of course, this energy, localized energy, is positive. So given alpha positive, non-negative, can we find a control such that the energy at time t in D is equal to alpha? So this is can you concentrate a prescribed value of the energy at time t in the domain D? Okay? Well, this was the initial question. Well, the energy, if you switch off the control, if you have no control from time, no control, if V is 0 after time t, then you have here conservation of energy for the wave equation, but in the whole set omega, not in D. So, except in the case D equal omega, the problem is instantaneous, as the energy is not preserved if the control vanishes after time t. The question of obtaining a prescribed energy on D for any time t greater or equal to t is completely open and quite interesting. Or maybe not exactly the same value, but to have the energy in D close to a given value alpha. This is a quite interesting problem. Of course, if we know the exact control, if we have conditions on little omega, to have exact controllability in the whole set, with the geometric control condition, then the problem is solved. This is not what is we are interested in. So we want conditions different from the usual one for global controllability. So now I will explain how to solve this problem and to have an equivalent problem. So first of all, we take Z, this Z, corresponding to, you have no control here, 0, but you have the initial conditions, Y0 and Y1. So Z does not depend on the control, and you have conservation of energy in the whole set, omega. So E omega of Z equal E omega at time t equal the energy at time 0, and this depends only on Y0 and Y1. And of course, the localized energy at time t is less than the energy in omega, because D is contained in omega. So we have this. ED at time t is less than or equal to E of 0 and Y1. Y0, Y1. And then we consider so we split the problem. We consider the problem, the wave equation with 0 initial condition here, but with the right-hand side, the action of the control acting on W. And of course, this problem is linear. So we have for every lambda, W of lambda V is lambda W of V. This is absolutely trivial. And now if I take the Y at the point lambda V, for the control lambda V, this is Z plus lambda W of V. Okay. Up to now, no difficulty. And of course, if I take the energy of that, it is the energy of the sum, and I can distribute this energy. So the energy of Y of lambda V at time t equals the energy of Z at time t plus lambda square, the energy of W, plus lambda, the double product, dz dt, dw dt, gradient Z, gradient W. Okay, well, so this depends on lambda like a second order polynomial, okay, and lambda square and lambda. So this term, well, I don't have time to explain, but this term, we can choose V. It's always possible to choose V such that this term is not 0. This term is not 0. Well, believe me, just believe me. And we will only consider such controls in the sequel. Now, what about this term? This term, if this term is 0, so if this term is 0, then you have lambda square something plus lambda. And of course, you choose the parameter lambda, you adjust the parameter lambda, and you have whatever you want on the energy. Okay? Okay. So this is not interesting. So we can consider this not 0 and this not 0. So the first thing is that if lambda goes to plus infinity, this term goes to plus infinity. So you can have this energy going to plus infinity. The question is, can we choose a control V such that this is minimal? So can we obtain V such that this is 0? And of course, if this is 0, it means that, because this is the sum, if we go back to the definition of the energy, this is the sum of the time derivative in d square plus the gradient of y square. So if this is 0, it means that this is 0 in v, in d, and the time derivative is also 0 in d. So this is exactly what we call localized exact controllability problem. So if we can solve this, then we have a v such that this is 0. And now adjusting the parameter v lambda, you can choose lambda. You go back to that. Well, we will show that this v is such that this is not 0. So then we can choose, you have a v such that this is 0, and then you can choose lambda such that excuse me, you can choose lambda such that I say it again. You can choose a v such that the energy of y is 0, but not the energy of w of v. Okay? So then you can choose lambda such that the energy any value you want between 0 and plus infinity. Okay? Well, so the question is, can we solve this problem of localized controllability? If D is equal to omega, this is the controllability, global controllability problem, and it is well known now, even if it's not completely standard. Well, but this is not what we want. If we solve this problem, it means that the W of V is equal to minus Z of T in D. So the time derivative is minus dz dt, and the energy of W at time t is not 0. This is what, if we can solve this problem, because the energy of Z is not 0, then the energy of W is not 0. So the same V is valid, the same V, the same control V is valid for any value of the energy just by adjusting the parameter, the amplitude, the parameter lambda, which is change. Okay? Now, we want to solve this localized controllability problem. We want to find conditions on omega and t such that there exists V with at time t, y is 0, and the time derivative at time t is 0. In D, only in D. Okay? Well, then we proceed as usual in these type of problems. So we will consider the adjoint problem. We take phi naught, which is H10 of D, and phi 1 L2 of D, and we extend by 0 in omega minus D. Okay? And we solve the problem, the adjoint problem, starting at time t. At time t, okay? We solve the backward problem from t to 0 in phi. Okay? Well, why do we do that? Now, well, in fact, we don't take this equation, but we take the equation for the time derivative. If you take the time derivative of the equation, it is the same for the boundary value. Of course, the time derivative at time t is phi 1, and the time derivative of the time derivative, which is the second time derivative, is the Laplace of the initial value. So if psi is equal to d phi dt, we have the wave equation for psi, and we have phi of t is phi 1, and d phi dt at time t is delta phi 0. Now you multiply this equation for y by psi, and we integrate by parts. Okay? So we have dy dt psi, which is phi 1, minus y at 0, which is y1, d phi dt psi, which is d phi dt at 0, minus y of t d psi dt at time t, which is delta phi naught, plus y at 0, y0, delta phi at 0. And this is, because you have multiplied the equation for y, this is the integral in little omega cross 0 t of the control times psi, which is d phi dt. So we want to have y of t is 0 and the dy dt is 0 in D. So we want this to be 0, because, okay, in D, because phi 1 is 0 outside D. So anyway, this says that this is 0. And phi naught is also 0 outside D. So we want y is 0 in D. So this is 0. So we want to have this 0 and this 0. So we want to have this equals this plus this. So we will have that if and only if there exists V such that this term is equal to this term minus this term minus this term. Okay? So the question is, does there exist V such that for any phi 0, phi 1 in H10 L2 of D, we have that? Okay? Well, now it is a question of functional analysis. This will be the case if this term is continuous for the norm of d phi dt. This will be the case if the left-hand side, so this means this term, is of the previous equality, is continuous linear form on phi 0, phi 1 in this space for the norm, this norm. If this is the case, which is the scalar, the norm associated to the scalar product, if this is the case, any linear continuous form can be expressed as the integral of V d phi dt. So there exists a V. This is the linear form corresponding to the scalar product d phi dt, d psi dt, and so there will exist V in L2 such that this equality holds. So, question, do we have that? Now, this term is less, okay, you integrate by parts here, you have gradient y naught, gradient phi naught, so gradient y naught, gradient phi naught, and here you have d phi, y naught, y1, d phi dt as 0. So, by Cauchy-Schwarz inequality, you have this inequality here. And this is the energy of y naught, y1, and this is the energy of phi at 0. In fact, I should put 1/2. 1/2, 1/2. Okay? To be correct. Okay. And this is optimal because you can, the initial data, y0, y1, can be chosen arbitrarily. Okay. So we have that. Now, you want this term to be less than or equal to, you want this term to be less than or equal to this term. Okay? Or equivalently, you want, well, first, sorry. Now, the energy of phi at 0 is conserved, the energy of phi is conserved in omega. So the energy of phi at 0 is equal to the energy of phi at time t, but at time t, the initial conditions are 0 outside D. So this is equal to the energy in D of phi 0, phi 1. Therefore, you want this to be less than or equal to this. So if there exists C such that for every phi 0, phi 1, we have this inequality, then there exists then this linear form that I was talking about is linear continuous with respect to the norm associated to that. And we have the existence of V such that this is valid. Okay? And the problem of localized exact controllability is solved. Well, so this is a standard argument that we use in controllability. But now the question is, do we have that? For which omega and t do we have, little omega and t, do we have that? Okay? For the moment, there's no solution. So the question turns out to be the following: under which conditions on omega and t do we have the previous localized observability inequality? So we introduce a localized geometric control conditions, which I call LOC-GCC, okay, LOC-GCC, which is the following. Every non-glancing ray of the geometric optics reflecting on the boundary of omega and starting from any point of d bar, this is essential, d bar, meets omega before time t. So what does that mean? What does that mean? It means that, well, I'm very bad at drawing things, but I will try to draw something. So if I take omega here, now if I take d here, what are the rays? So I start from any point in d bar, and I take the rays of any ray of geometric optics, you see, and reflecting on the boundary. Reflecting on the boundary, like this. And so on. And I want this to meet little omega before, okay. Sorry. Little omega before time t. Okay? So every, but this has to be for any ray here any array of starting from any point of d bar and has to meet omega before time t. Okay? Well, so this was and we obtained the following result with the previous notations. If omega and t satisfy the localized geometric control condition, then there exists C such that for every phi 0, phi 1 in H10, L2 of D, we have the, sorry, why do I, where is my screen? Where is my screen? Okay. Sorry. We have the localized observability, controllability, inequality, and then we have the localized controllability solved, and then we have the existence of a control such that we have a prescribed value, whatever alpha is, the prescribed value alpha of the energy in D. Okay? Well, there is a corollary. If you take any function in h1 of d, which can be extended to h1 0 of omega. For example, if d bar is included in omega, and sorry, this is not what I wanted. If d bar is included in omega, and d is regular enough, Lipschitz, then you can take anything in h1 of d. And if you have psi in L2 of d, we extend by 0 in omega minus d. So, and we call this set of functions E. Like that. So, if you have any psi naught, psi 1 in E cross L2 of D, then you can find a control such that you can reach at time t psi 0 and psi 1. This is a corollary for the proof. You just solve backward the equation from corresponding to the extension of psi 0 and the extension of psi 1. You solve it backward, and then you apply the theorem for these new initial conditions. Okay, this is not very important. Now, how do we prove the theorem? The proof of the theorem is not easy. The proof of the theorem, for simplicity, we exchange the roles of t and 0. We now want to prove that the energy of phi 0, phi 1 is less than the energy of the C0 d phi dt. But first of all, we want to prove a weak inequality, which is the energy in D is less than what we want plus an additional term here. But this additional term is compact, L2 H minus 1, and here you have phi 0 in H1 0 and phi 1 in L2, okay? The norm of phi 0 in H1 0 and the norm of phi 1 in L2. And here you have L2 H minus 1. So the weak inequality is the one we want plus a compact term. This is the major. Well, okay, this is one difficult part. We argue by contradiction. If not, if this is not the case, then you have a sequence of functions such that this is equal to 1 here, and this goes to 0, and this goes to 0. Okay? Well, so this equal to 1 means that this sequence is bounded in this space. And this goes to 0 because it's the sum of positive terms, means that this goes to 0, this goes to 0, and this goes to 0. Okay? So it means after extraction of a subsequence, we have weak convergence of phi 0 and phi 1 n to something. But we have, because this goes to 0, we have this goes to 0 in L2 H minus 1, and this goes to 0. Okay, but if this goes to 0 weakly, goes to phi 0, phi 1 weakly, and goes to 0 in L2 H minus 1, it means that phi 0, phi 1 is 0. Well, from this, we can also show that the gradient in little omega cross 0t, the gradient goes to 0 also. Well, we want to find a contradiction. we have the energy of that is equal to 1. But it goes to 0, 0 weakly. If we can show that it goes to 0 strongly, this will be a contradiction. Well, there exists a tool which is quite difficult, which is called the micro-local defect measure associated to that. Now we, of course, we mix, we associate to the initial values here the solution here. Okay, it is the same. If once we have the initial value, we have the solution. Once we have the solution, we have the initial value. So this micro-local defect measure measures how much it does not, the convergence is not strong, essentially. You see, if you have a weak convergence, but not strong, this measure, defect measure, is not 0. If this measure is 0, then the convergence is strong. Okay? So, but anyway, this micro-local defect measure exists. It is a radon measure on this, okay. It's a micro-local measure, so it is the space, time, and phase. Okay? And phase. But, okay, it should be n here because you have a phase associated to time. So it should be n here. And, okay, but we know that this goes to 0 and this goes to 0, okay? So this measure, this is the big norm. So the support of this measure is not contained in omega cross 0t. So the support is contained in omega minus omega cross 0t cross Sn minus 1. And we want to show that mu is 0. So as I said, this would ensure the strong convergence and lead to a contradiction because this is 1, and it cannot go to 0. Well, what we know about this local micro-local defect measure is that it propagates. Well, what happens? Yes, it propagates along the bi-characteristics of the wave operator. And the condition, local geometric control conditions, say that for every x0 in d bar, the bi-characteristics emanate. It's another way of saying this, this local geometric control condition. For any point x0 in d bar, the bi-characteristics emanating from x0 times 0 meets omega cross 0t, where mu vanishes. Therefore, well, if it meets a set where mu vanishes, then mu vanishes is 0 along the whole characteristics. So the whole bi-characteristic does not belong to support of mu. Okay. But now, if x0 is not in d bar, is in omega minus d bar, then you have, well, what happens is that this is the time, this is x, this is d bar, and you have x0 here, which is not in d bar. So the initial conditions have support here. are supported here. So the initial conditions are 0 in a neighborhood of x0. So, and the wave equation has finite speed propagation. So the solution is 0 in a neighborhood of x0t for t small enough. Okay? So the solution is 0 around here. So if the solution is 0, it means that the support of the micro-local measure, of course, it tends to 0. And the micro-local defect measure is 0 in here. Okay? So all the bicharacteristic emanating from here, they are 0. The mu is 0 on these characteristics. So, sorry. So if x0 is in omega minus d bar, the initial condition vanish in a neighborhood of x0, and from the finite speed propagation of the wave equation, the solution vanish in a neighborhood of tx0 for t small enough. This shows that, okay, for any phase t0, tau naught, psi naught, t x0 tau naught psi naught is not in support of mu. Then the whole bicharacteristics emanating from these points do not belong to support of mu. So whatever x0 is, if x0 is in d bar or not in d bar, all the bicharacteristics emanating from x0, 0 are not in support of mu. So the support of mu is empty set, and mu is 0. And so we have proved the weak inequality. Okay. Now we want to prove the strong, what I call the strong localized observability inequality. So we want to have that. And by a compactness uniqueness argument. So we know from the weak inequality, we know we have that. But this term is compact with respect to this term. Okay? So we have this greater than this minus something which is compact with respect to that. So because H10 L2 is compact in L2 H minus 1. So from the classical compactness argument, by contradiction also, if this is 0 implies that phi naught, phi 1 is 0, then we can drop out this term. Okay? So this is classical. Okay. Now the question is, what happens if this is 0 in omega cross 0t? Now let us define the set of initial values in D such that this is 0 in omega cross 0t. We call it n. We have to show that n is reduced to 0, 0. Okay. But in n, this is 0. So this is less than this. Okay? So in n, we know that for every phi naught, phi 1 in n, the energy is less than something which is compact with respect to that. So this is compact with respect to that. Well, if you have that, it means that n has finite dimension. Okay? Classical. Now it is clear that we also have, well, because we have open omega and 0t are open, if we have the inequality, we also have this for t minus delta, for delta small enough, okay? With a different constant, but C0 delta. Okay, we have that, the weak inequality. But now, if phi naught, phi 1 is in n, we take the differential quotient. We cannot take directly the derivative. We take the differential quotient for h small enough, phi t plus h minus phi t over h. And initial value and initial value for the derivative. So, okay, on 0t minus h, we have d2 psi h minus delta h is 0, psi h is 0 on the boundary, and the initial values are these ones. And, of course, this is 0 on omega 0t minus h. But we don't have any longer that. So we cannot apply the previous result immediately. But again, from the finite speed propagation, the initial values have support in d bar. So for a time small enough, for h small enough, all the solutions have support in d epsilon, where d epsilon is the d bar augmented by some epsilon shape. Okay. But on the other hand, we know that for delta small enough, and for every x0 in d bar, the bicharacteristic emanating from x00 reaches omega, okay, 0t open in t, so 0t minus delta. But d bar is compact. So, and this is open. This is open. So by continuity, this property is still valid for any point in d epsilon for epsilon small enough. Okay? So for h very small, for h less than h0, h0 small, and for every x0 in d epsilon, every bicharacteristic emanating from the x0, 0 reaches omega minus 0. So we can use the same argument as before and prove the weak inequality. But for psi h, you know that psi h, d psi h dt is 0 also. So we have this on psi h. For h small enough. But what we know is that, okay, psi 0 h, of course, converges in L2 to the time derivative of phi at 0, which is phi 1. And this converges in h minus 1 to the second derivative of phi at 0, which is the second derivative of phi is, the second derivative of phi is, of course, delta. Well, okay, is delta phi. Okay. The second derivative of phi at 0 is delta phi at 0. So, in fact, this converges strongly to d phi dt at 0, delta phi at 0, which is clear here. Okay. This is in L2, this is in h minus 1. So it means that this converges. So this converges also for h tends to 0. And it converges to what? It converges to, it converges to psi 0h converges to phi 1, and psi 1h converges to delta phi naught. So it converges to the energy of phi 1 delta phi naught. But the energy, which means that the limit of that is in H10, and the limit of that is in L2. It means that phi 1 is in L2, and delta phi naught is in H-1. No, sorry. It means, it converges in L2 and H-1. But this means that phi 1 is, in fact, is in H10, and delta phi naught is in L2. Okay? But we know that phi naught and phi 1 have support in D bar. So phi 1 is in H10 of omega, but 0 outside D bar. So it is in H10 of D. And delta phi naught has support in D bar, so it is in L2 of D, extended out by 0 outside. Okay. And now we have this with something which is in H10 in L2. And in fact, we have that because we have deep psi h dt, deep psi h dt, which is 0 in omega cross 0t, and it converges to that. So this means that phi 1 delta phi naught is also in N, in this N. So we started with phi naught, phi 1 in N, and we have that phi 1 delta phi naught is in N. Of course, we can repeat the argument. And we obtain that now delta phi naught, delta phi 1 is in N. Okay? Now, it means that minus delta maps N into itself. N is finite dimensional. It is symmetric, positive, definite. Therefore, it can be diagonalized in a finite dimensional space. And if N is not 0, you have eigenvectors. You have even a basis of eigenvector, orthonormal basis of eigenvectors, by definition not 0, 0, and lambda such that you have this, the same lambda for W naught, W1. So this is an eigenvector associated to lambda. So you have that. But if you have this initial condition, W naught, W1, then it is easy to compute the solution of the wave equation, which is this one. But now we want this solution to be in, to have the time derivative 0 in omega cross 0t, which means that for all t in 0t in omega cross 0t. And this is only possible if W naught and W1 are 0. Otherwise, you cannot have that.
Well,
yes.
Well, sorry for
okay.
Sorry for interrupting you. You have 5 minutes more, just to let you know.
It is finished.
Okay, no.
So
okay.
we have this N 0, and this finishes the proof of the result. Okay. Well, this was when alpha was 0, and then once you have that, this result of local exact controllability, you can have any value of the energy alpha between 0 and plus infinity. But when you require only alpha positive, not 0, it is easy to show that the only condition on omega 0t is that phi 0 in omega cross 0t implies 0, not in inequality. And this is much easier to obtain. Okay? Well, I will not speak of, okay. A very important open problem is the following. We have now considered the localized in space geometric control condition. But can we have a localized in frequencies? Can we also geometric control condition localized in frequencies? Namely, if you have a cone, we define as n-1 intersect a cone, and if you have the ray of geometric optics reflecting on the boundary starting from any point of omega, but only in this direction, outside this cone, which meet omega before time t, for which initial data do we have local exact controllability? This problem seems open, and in my mind, it is a very important problem. Okay, for Schrodinger equation, we do almost the same. The only point is that I go to the result. Now, if you have an open set and a non-empty open set D, if T is positive and omega is any non-empty open set of omega, for every strictly positive alpha, there exists V such that the solution Y of the Schrodinger equation satisfy this localized energy equals alpha. Well, you have essentially no condition on omega and T, but we need alpha to be positive. For alpha equals 0, the problem is open, completely open. We don't know any condition for that. And okay, and I think I will stop here. Thank you very much for your attention.
Okay, thank you very much for your talk, a very nice talk. And now we are open for questions. Some questions? So,
I have one question, please.
Okay, okay, Cortés, go ahead.
My question is, what is the solution when we consider the external forces in this equation? External forces in the physical reality situation.
External forces. You mean in addition to the control? You mean you have F plus V, something like that? If I go back, sorry. If I have a F plus V pi omega, do I understand correctly?
Yes, that is a question in the physical situation. Okay.
Yes, but I think this is not a real difficulty, because you put that in here. You put the F here instead of 0, and this is nothing to do with the control. So Z is well defined by the initial conditions in F. And well, you don't have that. You don't have that, but you have you don't have no longer valid. Okay, this is no longer valid. But we have this is plus something depending on f. Okay, on f squared. Well, that's all. That's all. After that, this is the same, and this is the same. Okay, no, there is no problem. This term is different, but not the term with lambda. Okay. Is my answer correct?
Yes, I understand. Many thanks. Obrigado, profesora Malta. Thank you very much. Thank you very much.
Muito obrigado, profesor Puel, por la excelente palestra. El profesor Puel es toda una eminencia al área de teoría de control.